Good morning. Already we have to see the partial differential equation and the Lagrange's linear equations problems and the videos also we have to see. Now we going to see the case study video of partial differential equation. We have to start the case study and the applications in the partial differential equation. First, going to start with the case study. Can you start it?
We are going to see the first sum that z is equal to ax minus by plus root a square plus b square. The given is x, ax plus by plus root a square plus b square. The differentiated partial with respect to the x. Now dou z by dou x is equal to a. The rotation of the dou x and dou x is equal to b. P is equal to a. This is the second equation. We are going to differentiate the partial with respect to the y. Dou z equal to dou y is equal to 0 plus b plus 0. Dou z by dou e, the rotation of q is equal to b. This is the third equation. We are going to substitute the second and third equation in the first. Z is equal to px plus qy plus root p square plus q square. We are going to see the second sum. Yes, a and x square plus b y square plus z square is equal to 1. We differentiate the partial with respect to the z. 2xa plus 0 plus 2x dou z by dou x is equal to 0. 2xa, we keep it on the left hand side, and we are going to the minus 2zb, the opposite side, which came the minus. We keep the a at the left side, and both 2 and x will be going to the denominator of the left side. The x minus zb by x. Differentiate the partial, differentiate with respect to the y. We get same. The b is equal to minus zq by y. We substitute the a and b in the first equation. We get z into z minus px minus qy equal to 1.
Okay. This one is the case studies. Next one, going to see the applications of PDEs. Start with applications.
First of all, the PDEs is a partial derivation equations, which involves in the partial derivation functions with respect to two or more independent variables. They are essential for modeling the physical phenomena. In the real-time world applications, they use for the engineers and scientific analysis and optimize the complex accurately. Why the PDEs are important? The PDEs are important in systems one or more than the variables. Changes occurs continuously. Physical laws such as conservation of energy, mass, and momentum applies.
Now we are going to see the major types of PDEs. There are three major types of PDEs: elliptic PDEs, parabolic PDEs, and hyperbolic PDEs. Elliptic PDEs are nothing but steady-state problems. Example: Laplace equation. Parabolic PDEs are nothing but time-dependent diffusion problems. Example: heat equations. And parabolic PDEs are nothing but wave propagation equations. Example: wave equations. And we are going to see the real-life applications of PDEs. First one, heat transfer. Predicts temperature distribution in rods, plates, and buildings. Used in air conditioning system, heat exchangers, and thermal insulation designs. Equations are used in here is heat equations. Next, sound and vibrations. Moral sound waves in air and rods. Applications are included musical instruments, noise control in diffusions, and earthquake analysis. Equation is used in wave equations.
Okay, next. Start.
So it's used in weather and climate modeling, used for describing the atmospheric pressures and wet velocity and temperature. So it's also used in fluid to study the movement of fluid and gases. Population dynamics is used as a model to spread the population disease and sources. So when we come to engineering application, in mechanical engineering is used to analyze the stress and strain of analyzing material, vibration of beams and plates. And when it come to electrical and electronics engineering, electric and magnetic field can be analyzed through this equation.
So, civil and engineering, structural analysis of bridges and buildings, groundwater, sewages and the soil mechanical, traffic flow and modeling. Followingly, chemical engineering, diffusion and the reaction process, heat and mass transformation of a reticle, pollution disperses in air and water, aerospace engineering, aerodynamic flow over the aircraft wings, heat transfer during the re-entries of the spacecrafts, stability and control analysis, numerical methods of PDE. Many real-world PDEs are the complex of the solving uses. Finite differential method (FDM), finite element method (FEM), finite volume method (FVM). These methods are implemented in engineering software tools in ANSYS, MET, MATLABs, and COMS SQL. Conclusion: the particle deficiency equations play a vital role in understanding and solving the real life and engineering problems. From the predicting weathers, designs mechanicals and analyze the electrical systems and controls the heat flow. PDE from the mathematics backbones of the modern engineering and science. Masters of PDEs enables the engineering to develop the shift efficiencies and the involves the solutions based on the real life chance. This is the final report of a case study based on the linear equations.
Thank you. Thank you.